Hello, everyone. I'm Norman Wahlberger. Thanks for joining me on this adventure towards studying research level mathematics. And here, in particular, in the direction of algebraic calculus and the geometry of de Castelao-Bezier curves. Today, a really interesting discussion because I'm going to be introducing all kinds of really important things. The first and most important computation in calculus, going back to Archimedes. And we're going to try to frame that in terms of the affine geometry of the parabola. So I'm going to have to explain to you this foundational topic of affine geometry, which on the one hand is essentially the geometry of parallels. That's one way of thinking about it. On the other hand, it's also the geometry of linear algebra. So it's actually very close to something that's very familiar to undergraduates, but the geometrical side is usually not so well understood. Usually people think of geometry as being Euclidean geometry, coming from Euclid's Elements. This kind of geometry is, in a way, sitting underneath Euclidean geometry. It's more fundamental. It's simpler than Euclidean geometry, actually. And it's in this context that I think calculus is best defined. This is the natural home of calculus, affine geometry. So we have to learn a little bit about it today. And I'm going to do that in a very hands-on way so that by the end of the lecture, I'll have given you a lot of information. And you'll be in a position to open up GeoGebra and do lots of calculations and actually start to investigate why the various things that I'm saying are true. You'll be able to derive a lot of the things that I'm saying, and with some additional work, you'll be able to discover new things yourself. Okay, so this is not entirely, but it's largely uncharted waters these days. Okay, this geometrical approach to calculus has laid dormant for a long time, and we are resurrecting it. All right, so let's have a look at a few formulas that we had in this situation coming from these control points, P0, P1, and P2. Okay, so we had coordinates for P0, P1, P2, and then we defined the Q points, Q0 and Q1, linear combinations of P0, P1, or P1 and P2, depending on some parameter, T. And then in terms of those points, we defined R0, corresponding to the same kind of affine combination of Q0 and Q1. And we saw that we could rewrite this in a number of ways. So we could express it as a affine combination of the 3 points, P0, P1, P2, with these coefficients, which are the quadratic Bernstein polynomials. We can also take this thing and expand it out as a polynomial in T, getting us P0 plus 2T P1 minus P0 plus T squared times P0 minus 2P1 plus P2. And this expression here will be particularly interesting for us to try and understand what the significance of that is. So one way of getting at that is to introduce some vectors. Let's introduce V0, which is the difference P1 minus P0. So that's effectively the vector from P0 up to P1. And then V1, P2 minus P1. So that's the vector from P1 to P2. So we're just marching along the de Castelao-Bezier polygon, if you like, okay, in the first vector and then the second vector. And now if we take the difference between these two vectors, V1 minus V0, well, we're going to get P2 minus 2P1 plus P0, which is exactly this thing that's appearing here. We could call it maybe A1. Because from a discrete calculus point of view, from a discrete physical point of view, if we think of a particle as moving from P0 to P1 to P2, etc., in a sort of discrete way, then these would be like velocities, and this would be an acceleration. Okay, so this term here has a natural interpretation as an acceleration. So we can rewrite this, if we like, as R0 equals P0 plus 2t times V1, there's V1, plus t squared times this acceleration A1. Now I want to do something just in addition here. I just want to observe that we can also rewrite this expression in a different way. I'm claiming that we can rewrite this as P0 plus t times P2 minus P0, plus now t squared minus t times P0 minus 2P1 plus P2. Let me actually check that I've done that right. how can I do that? So I can take this expression here and set it equal to this expression here. And I can ask Scientific Workplace if this is really correct. Can you check equality for me? Yes, it's true, says my computer. So I have done the algebra correctly. Now, when we look at it from this point of view, we see a different kind of expression. Here, we're thinking of R0 as what you get when you start from P0 and you go a certain way along a new vector now. Okay, the vector from P0 to P2. What would that be? That would be V1 plus V0. Okay, so maybe I should note that. Note that P sub 2 minus P sub 0 is V0 plus V1 in the notation that we've introduced. Okay, the sum of these two is this one here. So this is the vector from P0 to P2. So we can get to R0 by starting at P0, going in some direction in this direction. In fact, just T times this. And then some multiple of, again, this same acceleration vector. Okay, and comparing it to this, here this is telling us that we can get to R0 by starting at P0 and going some multiple of V0, the vector from P0 to P1, and then again some multiple of this acceleration vector. Okay, the rest we don't really need. All right, so this is a kind of an algebraic framework that I want you to keep in mind as we have a look now at the foundations of affine geometry in the context of this quadratic de Castellier-Bézier curve, the parabola. Okay, so I want to start out by explaining affine geometry to you in a very simple kind of way, from the point of view that affine geometry is really the study of points and lines under the notion of parallelism. So we have a notion of parallel lines, and more or less that's all that we have. Okay, so of the various tools, many tools that GeoGebra allows us, we're only going to use a very select few. For example, the equation for a line. Let's start there. So we have 2 points and there's a line joining them. And let's choose another line through this point here. And I'm going to make this point a little bit special because that's the meat of the 2 lines. Let's color it something else, say red. Okay, good. Now I can move these points around. Fine. So let me just tilt it a little bit here like that because I don't want you to think in terms of perpendicularity. So in this geometry, perpendicularity plays no role. Circles play no role. Okay, lengths and angles play no role. It's not a metrical geometry at all. If you know some rational trigonometry, quadrants and spread also don't play a role. So this is underlying Euclidean geometry, underlying rational trigonometry. It's sort of the foundation that we get. We start with affine geometry and then we build on top of it to create metrical geometries. All right. So what we are allowed to do here, however, is to create parallel lines. So these various constructions, we're not allowed to do pretty well any of them. Locus we'll do eventually, but other than that, parallel line is the main one. So parallel line. So let's take a line there and move it parallel through that point. That is a construction that we're going to be allowed to do. And similarly, if I grab that line, I'm still using the tool, I can make that point there. And so now I can create a point, an intersection point, intersect. I can intersect these 2 lines to get a new point. All right. So now I have a parallelogram. So parallelograms are key objects that we have in affine geometry. Notice that there's no coordinates around. Okay, I'm not using any prior numerical system, x, y axes or anything like that. We just have these points floating around. All right. So now I'm going to show you a crucial thing about how to extend this to create ladders or equally spaced kind of sequences of points. And so we grab the line tool again, and we'll make a line through those points, like a diagonal of our parallelogram. And then I'm going to create a parallel line from here through to this one. Okay, and then I'm seeing if I'm going to just make this point here, boom, where those two meet. It's a new point. And now I'm going to do another parallel line just to show you again. Also parallel to this one. Whoops, sorry. Let's get rid of that parallel line. Okay, there's the line through here, please. Thank you. And also a line. No, maybe not that one. I want to make a point here. Okay, and another parallel line, one more. Parallel to that through here, creating this point here. Okay, so what I have done here is I've created these equally spaced points along this initial line here. Okay, and you see that I've done that by starting with this parallelogram, which is rather arbitrary, and using the diagonals of this parallelogram. Okay, so this goes back to Renaissance artists. It's a fundamental kind of construction, actually, in projective geometry. Okay, but it's also very useful here in affine geometry because it shows you how to create a sequence of equally spaced points along a line. Okay, so in affine geometry, there's a notion of vector. So, for example, vector. Where's a vector? Here's a vector. Okay, so I can create a vector from 2 points. That point there, that point there. There's a vector. Okay, and then I could maybe even translate this vector. Maybe make a translate vector from point. So I'm going to take this vector and I'm going to move it to this point here. And you see that I've translated that vector. I've translated from here to here. So that's the kind of thing that working with parallels allows you to do in affine geometry. All right, so now I'm going to show you why this is important in terms of splitting a segment. So suppose that we have a segment. Okay, I can do it in the context of a line. So here's another segment. Suppose that I want to split this segment into 3 pieces. Okay, so what I can do is I can, let me take this thing here, okay, and escape. I'm going to make a parallel line to this one through here, okay, and I'm going to take this vector, the vector from here to here. Okay, and I'm going to translate that vector up here. Vector from point. So this vector, I'm going to move it over here. Okay, so this is now a copy of this thing here, except that it's been translated. Okay, so splitting this original segment into 3 is really the same as splitting this one into 3, because once I've split this one into 3 pieces, then I can translate back and split this one up. Okay, so let me show you how to split this thing up into 3 pieces. What I'm going to do is I'm going to use the fact that I have 3 equally spaced points along here, 3 actually equally spaced segments, and I'm going to take parallel lines. So I'm going to first of all make a line from this point to this one, okay, and now I'm going to draw parallel lines parallel to this through here, and also parallel to this through here. All right, and then this is the line I'm really interested in. Maybe I should just make it clearer. Okay, that's the line we're talking about. So along this line here now, I have got these new parallels and then the new points that I've created right here and here, those are going to split this segment into 3 equal pieces. Okay. So this is the beautiful thing about affine geometry, that just using parallel lines and these relatively simple drawings or constructions, we can split a given segment into an arbitrary number of equal pieces. So I could have done this, I could have split this into 7 pieces by starting with a ladder of 7 points and again using parallel lines. Okay, so in affine geometry, it's possible to split a segment into an equal number of pieces, and that's essentially allowing us rational coordinates. So, it's essentially what we're able to do here is multiply the original vector by a third. Okay, so this new vector from here to here is a third of the original vector, and this one here from here to here is 2/3 of that one. So correspondingly, I could create any rational multiple of this vector, like 17/39 times this vector. I could construct it in this fashion using just this framework of parallel lines. So affine geometry in this fashion is incorporating sort of rational arithmetic. Okay, and this, of course, is exactly the kind of thing that we're doing with the de Castelao-Bézier construction, because you remember what we did is we had a parameter, and we were taking a multiple of this point, actually 1 minus t times this point plus t times this point. So that's a multiple that's moving along here. Okay, that's exactly this kind of thing. We're basically taking multiples of this original vector. Okay, that's what you're doing when you're doing a de Castelao-Bézier construction. You're taking this point here, you're taking a vector like this one here, and you're adding to this point multiples of that vector. The multiple going from t equals 0 up to t equals 1. Okay, so we have all the ingredients now to be able to understand and to actually work with the de Castelao-Bézier construction of the parabola. Okay, so now let's have a look at this quadratic de Castelao-Bézier curve with control points P0, P1, P2, but now from the point of view of this affine geometry, where we allow ourselves the notion of parallel, but we do not crucially allow ourselves the notion of perpendicularity or distance or length or angle or quadrants or spread or any other metrical notions. Okay, so we are going to investigate this curve, and it's a very beautiful thing. But the first thing I want to sort of show you is that this construction that we had involved t going from 0 to 1. I can actually make that more general. There's no real reason to restrict ourselves to that range. So if I go from -3 to 3, 3 say, then, well, I'm getting more points. And now you can see it looks more like a real parabola, okay? And so, our control points, in principle, they could also, have t values which are less than 0 or bigger than 1. We would still get points on this extended parabola. Okay, so let's just keep that in mind. And I want you to keep that in mind because this is a parabola. Of course, it's a little bit tilted from the usual point of view. It's sort of like a tilted. Perhaps you can sort of see that this thing has an axis, and maybe I could try to zoom out. Okay, so I'm going to try to zoom out on this thing. Okay, so my parameterization goes up to a certain point. But you can kind of see that this thing here is like a very long ellipse in some ways, but it's not an ellipse, of course. These branches keep getting further apart. But there's still a sort of a direction in which this thing is going, okay? And that turns out to be a crucial property of a parabola, that it has a distinguished direction or an axis. Now, you might be used to thinking of a parabola in terms of a focus and directrix. Okay, it's important to let go of that notion. Okay, so we don't have a focus for this parabola. We don't have a directrix. We also don't have a vertex. But what we do have is this distinguished direction. Okay, and to fully understand that, I'm going to have to talk about points at infinity on the curve, and I'm going to do that in some subsequent lecture. That's a little bit more sophisticated because it involves some notions of projective geometry. Okay, but just at this point, you should appreciate that a parabola like this has an axis direction. In this case, it's roughly what I'm showing you here. Okay, so let me zoom in again, and I'll show you how to get that axis direction very simply, actually. In fact, we've already kind of seen it. Okay, so here we are, maybe one more. Okay, so here we are back in our land of our parabola, and I want to show you where this A vector comes from. So let me make some more parallel lines. Remember, that's one of the things we can do. So let's make a parallel line. So to this line here, I'm going to draw one through here. And parallel to this, I'm going to draw one through here. Okay, now that gives me then a parallelogram. P0, P1, P2, and then there's this fourth point down here. Now if I make that point something, so I'll intersect this line and this line, so I get that point there, and now I can make a line through P1 and that fourth point. That's like a diagonal of this parallelogram, okay? Then that is going to intersect here at the midpoint. So this is another way of slicing a segment, subdividing into two. Okay, I told you that, I showed you how to do it for 3. So you could do it also for 2, but this is somehow a more efficient way of slicing a segment into 2. Okay, so we've obtained this point here. Now, you remember what that vector that I called A was. The vector A was there was V0 and there was V1, okay? And it was V1 minus V0. So what would V1 minus V0 be? What's our vector? Where's our vector? Here's our vector. So that was the vector that had the form P2 minus 2P1 plus P0. Okay, so it's this vector here. That's that vector that appeared in our formula. So another way of getting, so this is the axis direction. So it turns out that this A vector that I told you about is actually the axis direction of the parabola. Okay? It's a distinguished direction in which this parabola is opening upwards to. And it's a purely affine notion. It is not a metrical notion. So you might say, well, where's the vertex? There is no vertex. Okay, there's no vertex. And all parallel lines, which are parallel to this one, have equal right to be sort of like an axis. Okay, there's no distinguished axis. There happens to be this one here because we've chosen these particular control points, but we could choose lots of other control points for the same parabola, and then we would get a different picture, but the direction here would always be the same. So this is some kind of canonical, important affine object in this story. So let's zoom out here a little bit. Okay. Now, having done that, let's move this. All right. The next order of business is I want to investigate what happens with this tangent. As we move our parameter around, you see our tangent's moving. Oh, okay. Actually, let me go back to our slider and just go back to 0 and 1. So I'm not outside the DCB story here. Okay, so now t is just running from 0 to 1 as before. So now a natural question might be, okay, suppose I have a point R0 on this DCB curve. How do I get this tangent? Yeah, this is a fundamental problem in the geometry of curves. Given a curve and a point on the curve, how do you actually construct the tangent? So that would be as follows. Suppose I rubbed off Q0 and Q1, and I rubbed off this line here, and you just had this parabola here and this point on the parabola. Could you recover this tangent direction? Well, that's a kind of an interesting question, isn't it? And I'm going to show you how to do that. Okay, so in the classical study of parabola, there are quite a few different classical techniques for constructing a tangent to a parabola at a point. I'm going to show you one which I'm not so sure how familiar it actually is, and whether it's actually even in the classical literature. But I don't dare say that it's not in the classical literature, because the amount of information known about these classical conics is just huge, even if a lot of it has been sort of forgotten or let to lie dormant for many years. So what we're going to do is we're going to make some constructions, and these are the kinds of things that you could do yourself. So if I gave you this problem, how do you actually construct Q0 and Q1 if you didn't know? Okay, you might want to pause the video and spend an hour thinking about it. So I claim that just with the ideas that I've already shown you, you can find a construction for this tangent. It's a great little exercise. It's fun. It's an exploration. All right. Okay, so you've spent an hour doing that, and now let's see if you agree with what I'm going to do. So what I'm going to do is I'm going to draw a parallel line through this axis direction through our point, because it's got to depend on our point, right? And now what I'm going to do is I'm going to look at this point down here where this thing meets, point, intersect. Okay, so there and there. This one and this one. Okay, so I have a new point of intersection. Let me just check that as I move this around, okay, that point of intersection on the base there is moving around with me. Okay, now what I'm going to do is I'm going to take, again, parallel lines. Okay, we can't use perpendicularity, only parallel. So I'm going to take this line here and through this point here. I get Q0. Oops. And now I'm going to do the same thing on the other side. So parallel line through here, through that point, and I get Q1. You see that? Fabulous. So we have constructed a tangent to the parabola at a general point on it in this DCB context. That's already quite a significant accomplishment. I mean, that is a major objective in classical geometry, is to create tangents to curves explicitly. And now I need to tell you about areas. Okay, so from my point of view, calculus is really embedded in affine geometry. And the reason is because area is intrinsically an affine geometry notion. Why is that? Well, remember, if we go back to that earlier worksheet that I showed you the basics of affine geometry for, and I created these parallelograms. I started with one parallelogram and then I kind of repeated it again. Once you have this notion of being able to repeat a parallelogram, then you have, in fact, a notion of area, a rudimentary but actually quite effective notion of area. So you can say, well, whatever this base parallelogram, its area is going to be, these other ones are going to have the same area. So to be more precise, what's really intrinsic to affine geometry is the ratios of areas. So for example, here, if I look at this this parallelogram right here, for example, let me actually just do this. So let me make a little polygon, okay? Here, 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 and here. Okay, that's a little parallelogram. Let's color it something a little bit more interesting. No, let's say green. Okay, there's that green parallelogram. Now, that has a certain area, and if I open the algebra sheet, I mean, then you see all kinds of stuff here, but don't worry about that. The last thing that I did was Q1, which is, what is Q1? It's a quadrilateral with polygon Q0, P1, Q1, and L. So that's exactly this thing. So in the underlying coordinates here, which you can't see, this parallelogram has area 10.47. Cool. So once we have this area, then we can compare other areas because we're able to translate, okay? And we're able to subdivide because we can divide segments by 2 or by 3 or by 39, okay? So we have an effective way of subdividing parallelogram areas into smaller parallelogram areas. And so if we can sort of cut and paste one figure into another, then we can compare their areas. So as a good illustration of that, let me make another polygon, okay, which is quite relevant to Archimedes. The triangle, which is inscribed P0, R0, over to P2, and back to P0. Okay, so that's a new parallelogram. Have a look. Have a look at it. There it is there. It's T1. Okay, this area here and this area here, the area of this reddish triangle that I've just constructed, that's T1, there it is there, 10.47. And the area of this parallelogram, that's also 10.47. Those are equal. And does it just depend on T? Let's see. As we move these around, you can see that these two numbers march along in lockstep. They're always the same. Okay, now let's have a look at them actually. Okay, so let's actually look at them. As I move this parameter t around, 12.25, 12.39, 13.02, okay, 13.2. Now at 0.5, my parameter is at 0.5, and now I have a value of 13.28. I'm going to go just a little bit further. I get 13.24. That is the maximum. So the maximum area is occurring exactly when my point R0 is on this distinguished axis through this middle control point. And that's also exactly the situation when the base of this this axis direction meets the midpoint of P0 and P2. And that's also exactly the situation when this line here is parallel to this. I'm going to convince you of that. One more parallel line. Okay, that line through there. There it is there. So there's something really special about this particular position on R0. This is, first of all, the midway point. Okay, it's the midway point for our parameter t. This is when t is equal to 0.5. It's also the place where the tangent is parallel to this base. It's also a place where this inscribed area is maximum. And it's that area, this area here, this triangle here, that is involved in Archimedes' famous result, which is that the parabolic area, which is the area enclosed by the curve and this base, is 4/3, exactly 4/3 the area of this thing here. Fabulous, isn't it? Okay, now I just want to point out something else. Yeah, so I've shown you this point here. And also I might just show you this other intersection here, the intersection between this thing and this line here. All right. So let's look at R0. So how can we get to R0? Well, one way is to go a certain direction in the direction of P1. And then come down in this direction. Now, what direction is this? Well, this is this axis direction, which is the vector A, the acceleration vector A that I talked about. Right? So this combination here corresponds exactly to that first expression for R0 that I showed you. Remember, it was P0 plus 2t times the vector P1 minus P0 plus t squared times the acceleration. Okay, there's the acceleration. T is 0.31, so we have to square it, and And this is going to be 2 times t. And then the other form for it is to go to R0 by first starting at P0 and going over to this point. So that's adding a multiple of P0, P2, the vector from P0 to P2, otherwise known as P2 minus P0. And you remember what that was? That was exactly t. So we start at P0, we add t times this vector, and then we go up, I think it was t squared minus t or something like that, times this a acceleration vector. So those different forms are actually corresponding to actual paths that you can see laid out here that we've created with the affine geometry, just using parallel lines. Okay, so this is a very rich picture, and I suspect that if you study it for an hour or two, or maybe a day or two, or maybe a week or two, you may very well discover some more interesting things about it. And you very well may discover some things which nobody has discovered before. Okay, so this is one of the joys of seeing a subject in a new light, is that we can explore really fundamental things and have a chance of discovering really basic, essential things which have sort of been left uncovered for centuries, or maybe even millennia. And now we're also in a really great position to talk about Archimedes' parabolic area theorem next time.